All right, well, let's see. So everything I'm going to talk about here is joint with Arpan Raksit and Dylan Wilson. Of course, thank you, for inviting me. It's really a spectacular conference. And I'm going to talk about some situation which is a generalization of something maybe a bit more classical. So suppose first that R is maybe sufficiently nice, something like smooth, or let's not go into this in the very first minutes of the talk, but some sufficiently nice, discrete, classical, in other words, commutative ring. Then one wants to study the algebraic K-theory of that ring. And at least since the work of Voevodsky, a very popular method for studying this would be to use a sort of slice spectral sequence, which has input something called the motivic cohomology of the ring. And this is supposed to be analogous to something like in a T.A.-Herzberg spectral sequence for topological K-theory, beginning with some kind of cohomology and ending with K-theory. But another very popular method for computing algebraic K-theory is to use so-called trace invariance. So there's a map to this other functor called Tc of R, and that maybe even further maps to something called Tp of R, or if you like, there's a trace to something called Thh of R. And this functor at least has a fairly simple definition. It can be defined as just this tensor product. But it really doesn't matter if you know what these functors are for now. I'll just say they're functors under K-theory, functors that K-theory maps to. And this one in particular is a very good approximation to K-theory. So this map is close to an equivalence by the work of Dundas, Goodwillie, McCarthy. And so in practice, computing Tc is a very practical way of understanding algebraic K-theory. So we have these two different techniques, the motivic spectral sequence and the trace methods. But it was an observation, very recent observation of Botmore and Schulze, that one can actually define motivic spectral sequences for all of these other invariants. So Botmore. Yeah, so I mean, I'm about to write the last sentence that I said. So Botmore and Schulze constructed these compatible motivic filtrations or motivic spectral sequences on Tc of R, Tp of R, and Thh of R. In other words, there's a spectral sequence converging to Tc where the input is something called the syntomic cohomology of R. And there's a map of spectral sequences from the motivic cohomology of R to the syntomic cohomology of R. And so, as you might expect, these two are very closely related, just as K and Tc are closely related. But we can also have a spectral sequence converging to Tp, and this has input what's called the prismatic cohomology of R. And there's a spectral sequence converging to Thh, and the input to that is, I'll call somewhat ahistorically, but I think nowadays, a few years after Botmore-Schulze, it's fair to call this the Hodge-Tate cohomology of R, just to give it a name. In any case, we can combine the trace methods with the motivic methods. There are these new motivic spectral sequences converging to these invariants. And the way that Botmore and Schulze define these is by the so-called QRSP descent. And this means a quasi-regular semi-perfectoid ring, which is a mouthful. And it's one that I don't want to need to consider. So the goal of this talk to construct in a different way from Blackmore and Schulze these motivic spectral sequences. So I want to give an alternative construction of these filtrations of TC, TP, and THH, which give rise to spectral sequences. And my alternative construction is going to work not just for a sufficiently nice discrete classical ring, but I want it to work for nice E-infinity rings. So what that means is that, well, the methods of both Matmore-Schulze and Morel-Voivodsky very much rely on classical rings and classical algebraic geometry. What I want to explain today is a way of constructing these filtrations that doesn't rely on classical algebraic geometry and can be phrased for an arbitrary E-infinity ring. And actually, THH is a lot easier than K-theory. So you might actually expect something like this to be easier to define and understand than the one on K-theory, and indeed that's the case. So I hope I can convince you that there's a very simple definition of this motivic filtration, and then these get progressively slightly more difficult to define as you go along. Yeah. So the question was whether these things collapse, and in general, no, they don't need to collapse. Well, I think in general, these don't need to collapse, even for classical rings or schemes, but in some cases they will, and they're always a method of computing. All right, so let me try to give a definition. So let me first give sort of a sort of maybe silly-looking definition. But if A is some E-infinity ring, then I want to define for every integer n a spectrum. So the spectrum I'm going to define, I'm going to call the nth piece of the even filtration on A. So some filtration on A. And the way I'm going to define it is I'm going to take the limit over all maps from A to B of E-infinity rings where pi star of B is even. And the limit I want to take is tau greater than or equal to 2n of B. So this is the Whitehead or Postnikov truncation of B. So every homotopy groups in degrees 2n or above, and this limit is over E-infinity ring maps into things that are even. Okay, so these Whitehead covers, these map to each other. Tau greater than or equal to 2n maps to tau greater than or equal to 2n minus 2. And so together, these spectra map to each other. And what we will see is that the fill n Eve of A, these pieces of the even filtration assemble into a filtered E-infinity ring. So they give a filtration of A, and that filtration is compatible with the E-infinity ring structure. So if you want to sort of formally define something like a big limit like that, you can do it with right Hahn extension. So another way of thinking about this, if you prefer, is that there's a right Hahn extension where we can take the even E-infinity rings that sits as a full subcategory inside of the category of E-infinity rings. And then if I have an even E-infinity ring, I can take these Whitehead covers and get a filtration, the filtered E infinity ring. And then I can take this right Hahn extension, and this right Hahn extension is this even filtration functor. So one of the things I've asserted here is that if A is even, so if it has even homotopy groups, then this fil star E of A is not very hard to understand. It's just the Whitehead or Postnikov tower. Right, and that's because if A happens to be even, this limit will have an initial object, and so it will be easy to evaluate, and you'll just get the Whitehead covers. But this is kind of a naive definition, and an immediate question is, if I have something that isn't even to begin with, so that this limit doesn't have an initial object, how would I ever go about understanding this filtration? What could I possibly expect to get out of this procedure? So let me give you a technique for calculating with this filtration. I'll put it on this board so we can keep it up. So I have to make a definition. So if A to B is a map of E infinity rings, we'll say that that is evenly faithfully flat or EFF for short, if the following property holds. So for every map of E infinity rings A to C with C even, I want to be able to take the homotopy groups of C tensor over A with B and get something that's even, and I want it to be a faithfully flat pi star C module. Okay, so that's just some condition for every map into an even ring. I want the push out to be even, and I want push out to be something like a free non-zero pi star C module. And the reason one makes this definition is that there's a proposition, which is not difficult to prove, which is that if we have one of these EFF maps, then we can understand the even filtration on A is the totalization of the even filtrations on the tensor powers, where that totalization is taken in the category of filtered E infinity rings. In other words, unlike this blackboard, we have descent for the even filtration. So this is sort of a formal thing from the theory of Grothendieck topologies. It's very straightforward to check this, but you might wonder, in practice, how many of these EFF maps do we have lying around, and how useful are they for computing this even filtration? Let's see. So let's do an example. So I can look at the unit map of complex Bourdism. So my claim is that the unit map of complex Bourdism is evenly faithfully flat. So what's the proof? Suppose I have some map from S to C with C even. Well, that map has to just be the unit map since it comes out of the sphere. Then we can calculate pi star of this tensor product, C tensor over S mu. And note that C is even, so it's complex orientable. So we have a Thom isomorphism. This is the same as pi star, or same as C star, if you like, of du. And again, C is even. The Atiyah-Hirzberg spectral sequence collapses. So this just looks like pi star of C, adjoin some variables, B1, B2, etc. So these are all in even degrees, and this is a free pi star of C module. So we've just checked that this map is EFF. Okay, as a corollary of that, we learn that we can compute the even filtration on the sphere as the totalization of the even filtrations on mu tensor over the sphere dot plus 1. In other words, the totalization of tau greater than or equal to 2 star mu tensor dot plus 1, because these smash powers of mu are actually even. It's easy to compute their even filtration. And so this is a hopefully familiar filtration on the sphere that we've constructed. This is the Adams-Novikov filtration. So in other words, the even filtration on the sphere gives rise to the Adams-Novikov spectral sequence. Why is this? I mean, so if you take the associated graded of this, you'll find you're exactly computing the Kovar complex for the E2 page of the Novikov spectral sequence, and you can go from there. Okay, maybe just a remark. Maybe I'll put that on the side here. Is that if A is any E infinity ring, then the map from A to A tensor over the sphere with mu is EFF. So that's completely formal. Once you know the map from the sphere to mu is EFF, if you just think about it. And it follows that if the mu homology of A is even, then the filtration on A is the Adams-Novikov filtration. So, in some sense, I've just redefined the Adams-Novikov spectral sequence for you. Maybe it's a little bit nice that I never mentioned mu or BP, I just mentioned the notion of evenness, and somehow the Adams-Novikov spectral sequence popped out. But for this to be really interesting, we need to understand that it's interesting in a case where the mu homology of A is not even. So let's look at one other example, just to give you a flavor of things. So if I look at THH of mu, which is just defined to be this tensor product, that maps down to mu. There's an augmentation map. And the claim is that this is EFF. So once you know this is EFF, it'll tell you that, again, because this is even, the filtration we're studying on THH of mu is exactly the descent filtration here. It's just the atom spectral sequence for this augmentation map from THH mu to mu. Okay, so how do you check this? Just to give you an idea of how you prove things are EFF. So I need to think about what happens if I have an arbitrary E infinity ring map from THH of mu to some C with C even, okay, so suppose I am in such a situation, then I want to study the homotopy groups of this pushout. So I take a C tensor over THH of mu with mu, and I want to compute the homotopy groups of that. So how might I do that? Well, there's a Tor spectral sequence. Right? There's a spectral sequence beginning with a Tor over pi star of THH of mu, pi star C, pi star mu. And one knows that this is just the Tor. What is pi star of THH of mu? It's an exterior algebra over mu star on a bunch of classes, sigma b1, sigma b2, etc., in odd degree. So the degree of sigma bi is 2i plus 1. This is an exterior algebra on odd classes, and we're taking Tor of pi star C, pi star mu. Okay, well, these are odd classes, and we assumed C had even homotopy, so they must map to 0 in C. That makes this Tor very easy to compute. This Tor is just going to be pi star of C tensored with the Tor over an exterior algebra, which is a divided power algebra. The spectral sequence will collapse, and what we see, it'll collapse for bi-degree reasons, and what we see is some kind of divided power algebra, but in particular, a free pi star of C module on even degrees. So this collapses and becomes a free pi star of C module, and therefore this map is EFF, and therefore the filtration on THH of mu that we're studying is this descent filtration. Okay, so let me write a theorem here. So if in Raxit and Wilson, suppose R is a discrete quasi-syntomic commutative ring. So quasi-syntomic here, that's referring to some kind of niceness condition. For example, any polynomial ring will be quasi-syntomic. The quotient of a polynomial ring by a regular sequence will be quasi-syntomic. Let me not spell out exactly the condition, but this is a condition that comes up a lot for Botmore and Schulze also. And the thing we prove is that this even filtration on THH of R is the same thing as the motivic filtration. Okay, so if you want to understand the filtration of Botmore and Schulze, you don't need to understand perfectoid rings or quasi-regular semi-perfectoid rings or anything like that. You just need to know what an even E infinity ring is, and then you're taking some limits. Okay, so maybe that sounds good here, maybe not as good in a number theory conference, but this is what it is. But this, yeah, so okay. So how? Oh, it worked. Okay. So let's make a definition. We say a connective E infinity ring is chromatically quasi-syntomic, to be in keeping with the theme of the conference, if two things are true, I want the mu homology of R to be even, and I want it to be quasi-syntomic. So if I take the mu homology of an E infinity ring, that's a graded commutative ring. If I assert it's even, it's just a commutative ring. I forget about the grading, it's just a commutative ring, and I want it to be quasi-syntomic, that same condition that comes up for Bott-Moore-Schulze. So under that hypothesis, we can go ahead and stick our neck out and make a definition. So if R is chromatically quasi-syntomic, go ahead and define the motivic filtration on THH of R to be the even filtration on THH of R. Okay, so that tells you how to make a motivic spectral sequence without any classical algebraic geometry. You just take this right-Kohn extension, the universal approximation by even E infinity rings. Maybe I should just remark that any classical quasi-syntomic ring considered as an Eilenberg-MacLane spectrum in degree 0 is chromatically quasi-syntomic. So this is a strict generalization. But there are other examples of quasi-syntomic things. So S, Mu, Ku, Ko, TMF, all of these things are chromatically quasi-syntomic. Right, and why is that? That's because if you take, say, the mu homology of one of these things, you're just going to get a polynomial ring. And a polynomial ring is one of these nice rings that is quasi-syntomic. Polynomial ring on even generators. Okay. So why is it that we feel like we're allowed to stick our neck out in this situation? What's nice about the property of being quasi-syntomic or chromatically quasi-syntomic? Well, we have the following result, which maybe explains why we focus on this class of connective E infinity rings. Here's a theorem. If R is one of these chromatically quasi-syntomic guys, then there exists, one can construct a highly non-canonical EFF map from the THH of R to B with pi star of B even. In other words, one can find a ring map into some even E infinity ring such that the motivic filtration is just the Adams filtration. It's the descent. So we saw an example of that with mu here. This map from THH of mu to mu is one of these EFF maps into an even thing. And this condition of being quasi-syntomic or chromatically quasi-syntomic arises because that's the kind of condition that makes it easy to write down maps like this into some possibly non-canonical even thing.
Yeah, just ask, if I've got a chromatically quasi-syntomic thing and I invert some stuff, is it still?
Yeah, but I think that's more or less right, but you have to be careful because connectivity is also something we kind of want in this picture, particularly because trace methods tend to be poorly behaved for non-connected things. Right, the question was what happens if you invert some things to this condition. Now let me make an additional remark. THH of R has some structure on it that you may or may not know about. It's a cyclotomic spectrum. It has an S1 action. It has a Frobenius. And one can choose B to be a cyclotomic E infinity ring. And the map to be also a map of cyclotomic E infinity rings. So there's an additional structure that one can find. One can choose one of these B's to be really nice. It can be cyclotomic. This map is cyclotomic, etc. All right. So then let's go ahead and make some definitions. We're going to define the motivic filtration on THH of R. Well, I said that in this chromatically quasi-syntomic condition, we're going to define it to be the even filtration. And then once we pick a B, maybe arbitrarily, we can just define this to be the totalization of tau greater than or equal to 2 star B tensor over THH of R dot plus 1. And so this doesn't look particularly canonical because it involved this choice of B, but somehow this formalism of defining things in terms of a right Hahn extension shows that this filtration is independent of the B we chose. Okay, similarly, we can define Phil star mote, for those of you who like these kinds of things, on TP of R. And we're just going to define it to be the totalization of tau greater than or equal to 2 star of this same object, B tensor THH of R dot plus 1 TS1. So the parenthesization goes like this. You take the Tate construction. In other words, you take TP, and then you truncate. And so it turns out that this is also independent of the choice of EFF cover.
Jeremy, sorry,
yeah.
you didn't address convergence at all. Did you want to say?
I mean, yes, it will converge. It will be complete and convergent under these hypotheses.
I guess more generally, we much less. I mean, I cannot clear.
Well, okay, so the question was about convergence. It will converge under this hypothesis, but we can talk about other things later. Okay, and then finally, Phil star mote of a TC of R. There's many ways of writing this, some of which look better than others. Let me just write the most economic thing I can so that it will fit on this blackboard, even though it will look maybe a little strange. It's the tau greater than or equal to 2 star minus 1 of TC of B tensor over THH of R dot plus 1. Okay. Turns out that's also a filtered E infinity ring. Not immediately clear from that definition, but anyway. So this gives you the motivic filtrations, and our theorem is that in the case where R is discrete and quasi-syntomic, this recovers all of these Bott-Moyer-Schulze definitions and all that. Yeah, of the cyclotomic spectrum. Just like this is TP of the cyclotomic spectrum. Okay, for those who know what all this stuff is. All right, I want to, maybe I can use this board. Let me just make a remark, is that the cosimplicial objects defined not the ones defined there, not on this board, but immediately preceding, they actually give stacks. So if you take the associated graded of these and compute pi star, you just get cosimplicial rings. Cosimplicial rings represent stacks. And so there are these stacks, R Hodge-Tate, R Prism, R Sin, and I'll just say respectively. So I'm just going over this sort of briefly, but the point I just wanted to make an aside here that these stacks, the one associated to THH, to TP, and to TC, these are actually the invariant, right? Not just the pi star of these things, but the stacks, the E2 page presented by the cosimplicial ring. Okay, and to give you an example, right? If I take S Hodge-Tate, this is the stack associated to the motivic filtration of THH of S. THH of S is just S. And this stack is MFG, the moduli of formal groups. All right, that's the stack associated to the Adams-Novikov spectral sequence. All right, so I succeeded in my goal of not having to erase the board. So what I want to do is in the next few minutes, I'm just going to go really quickly through some examples showing things that one can do or people are in the process of doing with this motivic filtration. And I'll try to go quickly, and then people can have a longer coffee break if they want, or see enough now to ask questions if you're interested. So let's see if I can get this to work. Just going to take a moment to turn on. Oh. Okay. All right, thanks. Thank you. All right, so okay. So I just want to give some examples. So, you know, THH of the sphere is the sphere. This is the most basic example you'd want to understand. And we saw that there's this EFF map from the sphere to MU. That's an example of one of those maps from THH of R to B. And I said we can make these things cyclotomic. In fact, we can make that one cyclotomic if we just give MU the trivial cyclotomic structure, because THH of the sphere also has trivial cyclotomic structure. And what that means is that the stacks giving the motivic filtrations of THH, TP, and TC are all extremely explicit. This one is the Adams-Novikov filtration, but in general, you can just write down in E1 page a cobar complex type thing associated to this particular choice of EFF cover from S to triv MU, and that's very explicit to calculate with, so we did some calculations at some AIM workshop. But one thing to notice is that you might wonder, what is the motivic filtration on TC of the sphere? And it turns out to be this thing. This is not maybe the most exciting thing you would hope for from a motivic filtration on TC of the sphere, because it's not doing too much. It's just tau greater or equal to 2 star minus 1 of the MU tensor dot plus 1 of TC of the sphere. So this is basically the Adams-Novikov spectral sequence, but it's a little bit different from the Adams-Novikov spectral sequence. It's different in a somewhat interesting way, which is important when it comes to the comparison map, the unit map, into classical rings, which we expect to be filtered compatibly by things like Voevodsky's filtrations. And the key difference between sort of the classical Adams-Novikov for TC of the sphere and this is that some of the cells get bumped in filtration. So for example, this bottom cell is put into filtration 1 instead of filtration 0. I'll try to show some pictures in a moment.
Can I just ask you,
Yeah.
what exactly are you claiming about the Adams-Novikov? I mean, I would say that the Adams-Novikov filtration I would normally say is not well defined until you get to like this E2 page corresponding to spectral sequence.
Yes.
But you're claiming a specific, more specific filtration.
Well, so if you take the pi star of the graded of this thing, you don't get the E1 page, you get the E2 page. So this filtration only knows about the E2 page. and it is canonical in the same sense that you're saying.
So, I mean, can you just say in more classical terms, what is the nth stage of that filtration?
It's the totalization of pi 2 star of this thing. But if you look at what that totalization is doing, it's computing the Kobar complex. Like if you actually go and compute pi star of that totalization, you'll find you're doing the Kobar complex computation that computes the E2 page. I mean, we can talk more about it later. Okay, so here's TC of the integers, mod 2 in V1. This is the motivic spectral sequence for TC of the integers, and it has, you know, if you're working at the prime 2, it has only these 5 dots. So if you mod out by 2 in V1, this is a F2 vector space on 5 elements. So this class that's called lambda 1t, it's in stem 1 and Novikov filtration 1. So that's the right place for eta to appear, and that is indeed eta. And actually what it is the image of this brackets T1, right? So it's more than just eta, it's the exact Adams-Novikov E2 element that detects eta, because this really is kind of like an Adams-Novikov E2 page that I'm drawing a picture of. Just to remark is that this class partial lambda 1, it's the product of partial and lambda 1, but it's also eta squared. So there's some interesting multiplicative relation that lambda 1t squared is partial lambda 1, and that's a kind of Poincaré duality. And TC of the integers is related to Ital cohomology of Q, and this is some kind of Tate duality. This partial here detects the bottom cell under the unit map. So in particular, in order to have Tate duality, in order to have this nice picture where you see a Poincaré duality group, it's important to put partial in filtration 1 and not in filtration 0, where it would be in the classical Adams-Novikov spectral sequence. This class lambda 1 is something that exists in TC of Z, but is not in the image of the unit map from TC of the sphere.
Sorry, Jeremy?
Yeah.
The bottom cell of the CP infinity -1 is detected, is that what you're saying?
Yeah.
Okay.
So that's in degree -1, right, which is the degree of partial. Okay. So here's the picture of TC of the complex K theory, mod 2 V1 V2. I just put that up to show you that it's very similar to the picture of TC of Z. And this kind of picture was really predicted by Rognus and Asunian Rognus, and was a great inspiration for all of this. I guess they drew some nice pictures of what the motivic spectral sequence might look like, maybe at larger primes. Yeah, so I just wanted to point out some property of this. Once you know what this looks like, mod 2 V1 V2, then you can start running Bachsteins to figure out what it looks like integrally. And for just degree reasons, the first Bachstein, the V2 Bachstein spectral sequence, has to degenerate. And that means that all of these classes become generators of F2 adjoined V2 modules, and this thing is a free F2 adjoined V2 module. And that property was really highlighted by Rognus a long time ago. We call it pure FP type. And it's an important property that this first Bachstein spectral sequence degenerates. Okay, let me show you. This is the picture at the prime 5, so it's a very similar picture, but this is the atom summand instead of all of Ku, which is also chromatically quasi-syntomic, and I've modded out by 5 in V1. And I get a similar sort of Poincaré or Tate duality. You see here still partial infiltration 1 in some of these classes. Let's see, what did I want to say about this? Right, again, the motivics, so once you have this filtration, as we was asked earlier, does this filtration that converges to TC actually collapse? And in this case, it does for degree reasons. So you can compute V1 star of TC of L, this computation of Asunian Rognus, just by calculating the E2 page of this spectral sequence, which is what this is a picture of, and for degree reasons, observing that it must degenerate. If you want to push further, you want to probably run some of these Bockstein spectral sequences past the V2 Bockstein. So you'd want to run the V1 Bockstein and then the 5 Bockstein in order to get sort of integral information. And so the very first Bockstein differential you can get just from the standard Kobar complex manipulations. So you're really supposed to think of these as variants of Adams-Novikov spectral sequences, and a lot of the formulas you know go through exactly the same way. And in this case, there's a V1 Bockstein differential on V2 that's going to hit V1 T1 to the 5. T1 to the 5 is T to the 5 lambda 2. And so you can just read off the formula for that first Bockstein differential. And the next thing you'd want to compute is the Bockstein differential on V2 to the 5th. So if you go look in Asuni and Ragnus's ACTA paper, they end with a discussion asking sort of what is this Bockstein on V2 to the 5th. So that's the final question that they leave open at the end of their paper. And you can calculate it using this formula for A to R of V3, kind of interestingly. So if you use A to R of V3, you can learn the Bockstein differential on V2 to the 10th. It's not so easy to directly learn the Bockstein differential on V2 to the 5th. However, this whole thing is V2 torsion free. So if you know what happens to V2 to the 10th, you know what happens to V2 to the 5th. So really this purity, this V2 torsion freeness is really useful when doing these Bockstein spectral sequences, because what one can read off from the sphere is often things in high degrees, but they can be pushed back using the torsion freeness to understand the Bockstein in complete generality. So I'll just say something very vague, that these Bockstein differentials, they get a bit complicated. So you see inside of this a picture of more or less the Bockstein spectral sequence for half the K2 local sphere, for the fixed points of the kernel of the determinant of the stabilizer group. And so that's pretty big. You know, it's a complicated thing, but it's something that you can relate to a known object, namely this Bockstein spectral sequence for half the K2 local sphere. And I think this was also noticed by Robert when he was looking maybe at our paper, I don't know. Right, so just a comment on these Tate dualities. So these Tate dualities are studied a lot right now, even just by pure number theorists. So when we saw the Tate dualities in the pictures, those had to do with the cohomology of these stacks. But in fact, there's a kind of Tate duality for any perfect complex on the stack. And this is recent work of Bhargav Bhatt and Jacob Lurie. And they develop a version of this Tate duality for an arbitrary complex sheaf on this stack that filters TC of the integers, or the p-adic integers. And those complexes have a number theoretic meaning. The complex on TC somehow encodes, upon inverting V1, a Galois representation, as it must, since the V1 inverted TC is Étale cohomology. But it's a particular kind of Galois representation that comes from a class that's supported on TC of Z as opposed to the V1 inverted TC. And that's some crystalline condition, which is apparently of a lot of interest to people like Bhargav Bhatt these days. So you can read a lot more about this duality in Bhatt's ICM address and his notes from the recent course he taught about it. And it looks like it's fairly straightforward to generalize this quite a bit to some of these other stacks where we saw, at least at the level of cohomology, this multiplicative Tate duality. Okay, maybe one final comment is that you might ask, what can we do for non-commutative rings? So I think Piotr, in the last talk or so, is going to give one thing you can do with non-commutative rings, which is really cool. Here's a sort of other thing you can do, is that if you have, say, a complex-oriented ring, if it's just E1, then it's hard to talk about the even filtration on it, because that was only defined for E-infinity rings. However, one can study some kind of filtration on its TC, and when you study that filtration, what you're seeing is the cohomology of a sheaf on this MU syntomic stack. because this thing was an MU algebra. So that spectral sequence involves not just the ring, but the choice of the ring with its complex orientation. But that data of a map from MU to an E1 ring gives you a spectral sequence associated to this syntomic cohomology of MU. And this thing was more or less what came up in at least half of the proof of this Quillen-Lichtenbaum conjecture that did with Dylan Wilson for BPN, where BPN is notably not E infinity by Tyler Lawson and Andrew Sanger's work. So one needs to do something more like this sheaf cohomology thing, maybe, or Piotr will tell us a better story. But yeah, so that can be useful. In particular, the only co-author who is actually here for any of this is Gabriel Angelini-Knoll, where we've been thinking about what this sheaf looks like from Morava K-theory, which is connective Morava K-theory is a complex-oriented ring. And so not just I, but I think he would be very excited to talk about that to anyone who's interested in this stuff. I hope it's at least vaguely interesting, and maybe I'll just stop here.